When I started our lecture about bases, I talked about systems of coordinates in the plane. And in particular, I said that we could represent the plane as the vector space R squared, and that there was a standard way of coordinatizing R squared, in which the vector 1, 0 corresponded to a unit length vector in a horizontal direction, and 0, 1 corresponded to a unit length vector vertically, as I've drawn there. And what made these vectors suitable for use for coordinatizing was the fact that you could write every single element of R squared uniquely as a linear combination of 1, 0 and 0, 1. And in fact, you can choose lots of different systems of coordinates. So if you choose any two vectors in R squared which form a basis of R squared, so they do not have to be at right angles, anything like that, then it turns out that they still have this same property that you can write any vector in R squared in one and only one way as a scalar multiple of f plus a scalar multiple of g. In fact, that property of unique representation as a linear combination applies to any basis of any vector space. That's what we're going to prove on this slide. So what our statement here says is that if you have any basis v1 up to vn of a vector space v, then every element of v can be written in one and only one way as a linear combination of v1 up to vn. So the fact that this element v and v can be written as a linear combination of v1 up to vn is just true because a basis has to be, in particular, a spanning set. So v1 up to vn is a basis, so it is, in particular, a spanning set. So all we have to do is show that there is no other way to write v as a linear combination of the v's. So let's suppose we have two representations for v as a linear combination of our basis v1 up to vn. So our first representation was L1v1 plus L2v2 up to Ln_vn. Let's suppose we have another representation of this as a linear combination of v1 up to vn. So this time we will call the scalars in this linear combination m1 up to mn. Then what we must show is that actually L1 is equal to m1 and L2 is equal to m2, and so on. Well, if we have this equality, we can use the vector space axioms, in particular the associativity rule, the commutativity rule, and the distributivity law for scalar multiplication, to rearrange this to say that L1 minus M1 times V1 plus L2 minus M2 times V2, and so on, is equal to the zero vector in V. But then this is a linear dependence relation on the basis v1 up to vn. But a basis is in particular a linearly independent set. If you've got a linearly independent set, then the only linear combination equal to the zero vector is the linear combination where all the scalars were zero. So it must be that L1 minus M1 equals 0 and L2 minus M2 is equal to 0, and so on. And that means that every Li is equal to the corresponding Mi. We've completed our proof because we've shown that there's only one linear combination of the VI's equal to a given vector. Before I move on, let me just say what this allows you to do. So this allows us to compare coefficients. So what I mean by compare coefficients is that if you have two linear combinations of a basis, so let's use the same notation for our basis as before. So let's suppose if AI, the sum from I equals 1 to n of AI VI is equal to a sum from I equals 1 to n of BI VI, then you can compare the coefficient of V1 with that of B1, and they must be equal. And similarly for V2, V3, and so on. So A1 must be equal to B1, A2 must be equal to B2, and so on. That's what people mean when they talk about comparing the coefficients. If V1 up to Vn, in fact you only need it to be a linearly independent set, then you can compare coefficients in this sense. On the final slide, I want to talk about why it might be useful to have multiple different bases for the same vector space. So as I've said, the same vector space can have many different bases. In fact, in general, it might even have infinitely many different bases. So why would it be useful to have more than one basis? Well, the answer is that having two different bases gives you two different ways to look at the same underlying object. So I will try and explain by giving an example why that might be useful. So linear algebra is one of the most useful pieces of mathematics you can learn. It's used in all kinds of different areas of mathematics, pure and applied, and all different applications of mathematics. One of the places that they use it is in representing images in machine learning or in data representation. So we're going to look at the simplest possible way to images, which are images consisting of two squares next to each other like this. And our images are just going to be black and white images. So each of the squares can be somewhere between completely white and completely black. And we're going to represent those as vectors. So we might represent our images as vectors A and B, where the first entry, A, tells you how dark the first square was, and the second entry, B, tells you how dark the second square was. So we might represent something which is very light coloured by a very negative number and very dark coloured by a very positive number. For example, this particular image might correspond to something like the first square is very light, so it might be minus 1,000. And the second square is fairly dark, so it might be something like 50. Something like this. So what we have is a basis for r squared, which is the basis 1, 0, and 0, 1, the standard basis. And we called this E1 and this E2. And we're now saying that AE1 plus BE2 represents an image where A1 tells you how bright the first square is, and BE2 tells you how bright the second square is. Well, of course, we know that there is another basis for r squared. So r squared has another basis, one 1 and 1 minus 1. So let's call this F1 and let's call this F2. That was one of the examples on our very first slide about bases. So we should be able to write every element as r squared in one and only one way, as a linear combination of f1 and f2. So we could take this vector here, we could take this vector here, which I will now draw a more careful line, and we can rewrite it as a linear combination of the f's, as a linear combination of our second basis here. So if I do that, well, what you can check is that you can do this as a plus b over 2 times f1 plus a minus b over 2 times f2. Let's just see if that is correct. So if I have a plus b over 2 times 1, 1 plus a minus b over 2 times 1 minus 1, then if you work that out, that is, in the top place I should get a plus b over 2 plus a minus b over 2, which is a. In the bottom place we'll get a plus b over 2 minus a minus b over 2, which really is b. So this really is correct. Okay, so I can do this. I can represent this same vector ae1 plus be2. I can rewrite that as a linear combination of the f's. What is this telling me then? I mean, what does this mean? So in our old representation, just here, a was telling me how bright the first square was, and b was telling me how bright the second square was. So what have I got now in my representation with respect to this second image, with respect to this second basis? Well, the first coefficient there, a plus b over 2, that has a meaning in terms of the brightness of our image. A plus b over 2 is the average brightness of the two squares. So this thing is the average brightness. And the second coefficient here is also telling us something meaningful about the image. It's telling us about how different the two squares were. Right? If they were the same brightness, then this coefficient would be 0, because a will be equal to b. But if they were very different, then a minus b would be very large. So this is telling us how different the two squares are. Therefore, these two different bases, E1 and E2 and F1 and F2, are giving us really meaningful different ways to look at the same image. The representation in terms of the first basis is one where the coefficients tell you how bright the first square is and how bright the second square is. And the representation in terms of the second basis, F1 and F2, in that representation, the first coefficient is telling you how bright the image is overall, so what's the average brightness of the two squares, and the second coefficient is telling you how different the two squares are. And both of those give you a different way to represent the same image. That's in general why multiple bases are a useful thing to have. They give you different ways of looking at the same data.